Hello, here's another lecture about cosmology. Yeah. Okay, so we're going to talk about gravitational lensing, and by where I mean me. So let's see, what does this have to do with anything? We've been talking about dark matter, and we've talked about galactic rotation curves, we've talked about clusters of galaxies, analyzing the motions of galaxies within clusters to determine the gravitating mass therein. And it's also worth talking about the phenomenon of gravitational lensing and how that can be used to also determine the mass of objects in particular clusters. So this is not a GR course, but let me at least just paint a sort of broad brush picture for you. The theory of general relativity is a theory in which basically matter and energy are put into the Einstein equations, and they are used to determine the space-time curvature. And so that's sort of, you can think of that as like an arrow that goes from left to right. But it's also true that space-time curvature has an effect on the motion of particles and waves and fields in general. And so not only can matter and energy tell space-time basically how to curve, the space-time curvature tells matter and energy how to move about. And so some equations that you may have seen before, and we won't actually need to calculate anything here, but just so you're aware, this Einstein tensor, g mu nu, which itself has, because it's symmetric, I suppose it has 10 independent components in 3 plus 1 dimensions that we live in, 3 spatial and one time dimension. But this equation, g mu nu, on the left-hand side, it basically is a function of derivatives of the metric. So this is a dynamical equation, and in Einstein's theory, this is equal to 8 pi g over c to the fourth times the the energy momentum tensor T mu nu. So these subscripts just correspond to different components of these tensors. This is these represent the Einstein field equations, and again, that's what the equations that inform us how matter and energy make space-time curvature curve the way it is. So in principle, you would take these equations and solve for the metric g mu nu. Okay. Right. So going the other way, though, space-time curvature can affect the motion of particles and fields, and the way that that looks it involves something called the geodesic equation, and basically this is a statement that in the absence of any other forces, a particle, in particular a point particle, will follow the path, if you like, in quotes, the straightest path, or the path of, see, the way that this works is actually if it's a massive particle, the proper time is maximized, and if it is a massless particle, you can at least say that the space-time interval from its initial point to its final point is extremized. Anyway, it's an extremization problem, and if you've taken classical mechanics, there is actually a Lagrangian you can write down for a point particle, and I'm happy to talk about that in office hours. But in the end, what you get is an equation of motion for a particle, and it looks like this. It's the second derivative of this position variable x mu, and just for you to see, this x mu has 4 components. There's sort of a, like a time component, an x component, a y component, a z component. That's the way you can think of it. So that gets added to something called the Christoffel symbol. Itself is not a tensor for reasons that I'm not going to go into now. But this complicated looking thing is really a giant sum over the index alpha and the index beta. And this parameter s, you can in fact think of this as the space-time interval, if you wish, or just the sort of any good parameter that it's sort of, as it monotonically increases, the position of a photon goes from point A to point B. Anyway, if there are no other forces present, so it's just gravity, space-time curvature, then this is equal to 0. And then one can solve for, one can take this equation and in principle solve for x mu as a function of this parameter s, or any other parameter that is good. So in other words, you can solve for the trajectory of a particle, a proton, electron, a photon. Okay, so that being said, we want to talk about gravitational lensing. The first thing I want to do is just let you know that one of the most important solutions to the Einstein equations is actually the spherically symmetric vacuum solution. So you imagine that you're in some part of space-time, you're in a vacuum, and you know that there's spherical symmetry, but there may in fact be something, some distribution of matter or energy nearby, even though you yourself are in a vacuum. And so the most important example of this would be more or less the space-time around the Earth or the Moon or the Sun. So you're more or less in a vacuum, and it's more or less spherically symmetric around that object. So that vacuum solution is called the Schwarzschild solution, or the Schwarzschild metric. Let's see if I can get the spelling right. Schwarz or Schwarzschild. Right, so we won't derive this, but the way that the metric looks like, this ds squared, you can write this as we call this the contraction of g mu nu with dx mu and dx nu. That is to say that this tensor g mu nu, the metric tensor, sort of, if you like, it's sort of dot producted into the infinitesimal changes in coordinates, whatever, that's ds squared. And the way that this looks like is in some ways should look familiar to you. So there's a c squared and a dt squared, and there's a minus sign, but the difference is there's a factor of 1 minus rs over r. That rs is called the Schwarzschild radius, Schwarzschild radius. And then there's another term that looks very similar, 1 minus rs over r to the minus 1, and dr squared plus r squared d omega. And that is called the Schwarzschild metric. Now I should say it's in a certain set of coordinates. You can change your coordinates just like you can change from Cartesian to polar to whatever you like, and then the metric looks different. But at least in these sets of coordinates, this is the solution. And you can verify this, by the way, that whatever this Schwarzschild radius is, rs, if it was set equal to 0 exactly, then you would recover your normal Minkowski metric that we might have talked about earlier on in the semester. That's just the metric for regular old space-time that you might have seen in a course on special relativity. In any case, this Schwarzschild radius is related to the mass of the object that is at the sort of center of your analysis, or at the origin of coordinates. The thing that's centered around r equals 0, and it's given by 2 times Newton's constant times the mass divided by c squared. And if you check the units, this should have units of length. Just for example, the Schwarzschild radius of the Sun, that's what this means, a circled dot. Remember, that's for our own Sun. You would stick in the mass of the Sun there, and you can verify that this is approximately 3 kilometers, or if you're a little more careful, 2.95 kilometers. So I've starred this to remind you that this is actually something I think you should just go ahead and plug it in your calculator to check. Just for your own sake, remember g is equal to 6.67 times 10 to the minus 11 in the right units, newtons times meters squared divided by kilograms squared. So I'll let you write that down. And the mass of the Sun, to 3 sig figs, I don't have it off the top of my head. You can look this up, of course, but it's at least 2 sig figs. It's 2.0 times 10 to the 30 kilograms. You should get that third digits to verify that really the Schwarzschild radius is, to 3 sig figs, 2.95 kilometers. But if you want to just remember, 3 kilometers. By the way, this Schwarzschild radius, this would tell you the radius of the horizon if this was actually a black hole. If you took all the mass and jammed it in to a distance below the Schwarzschild radius, this would also be the metric for a black hole. And that tells you that if the Sun were to somehow collapse and all the mass ended up going down and it turned into a black hole, the size of the Sun, in some sense, would only be about 3 kilometers. So it would be like a sphere with a radius of 3 kilometers. Okay. Anyway, so something that I've already said, curved spacetime means that that objects like just general particles or a photon, in the absence of any other effects, they just follow the shortest paths through that spacetime. In some sense, you could call that's like the straightest path. But what that means is that if it takes the shortest path, that means that spatially that will very likely be curved, right? Because not only is there a spatial curvature, there's a sort of curvature associated with time, and to get from point A to point B, the actual path it might take to minimize, to extremize this action that it obeys, will end up with a spatially curved path. Okay, so here's a crappy picture. Actually, it's not so bad. Imagine that there's a big central mass that I'll call capital M. And I've set up these orange lines here. I wish they could be dashed. They're not. But they're supposed to represent asymptotes. So what I imagine happening here, given, of course, that right gravity is attractive, and maybe I'll set it up like this. You imagine that there's a photon coming in. Starts over here. It's coming in, it's very far away, and then as it approaches this massive object, right, it gets bent toward it, unsurprisingly. So here's the path, and then it gets curved toward it, and it keeps going, and then so these are asymptotic lines that I've indicated just to give us a sense. Whee, and then it goes off to infinity. So it starts over here. I'll put initial, and it ends up going, off this way, and that's sort of final. But in the process, its trajectory has changed. It's been bent by some angle that I'll call alpha, because I think that's what Ryden has used. And just to label a couple things, notice that there's a so-called impact parameter, which is the perpendicular distance from the initial trajectory to the location of the gravitating object. That's called B. Now, you'll notice, though, that is not the distance of closest approach. Technically, that would be this distance measured here, which I'll call R0. So B and R0 are not identical, but they're not very different. So actually, as it turns out, that approximating B as R0, I've exaggerated the picture as I've drawn, but they're pretty damn close to at least the order of approximation that we are working to here. Okay, so you might guess as to what the final answer has to look like. So let's just think about what this means. If we want to know what is alpha, you want to make a guess as to what alpha has to be. Given all the things we have at our disposal, we have, so you imagine this is going to somehow be a function of the mass of the object, but it's a gravitational effect, so there's got to be a g in there. And actually, we already know the metric of such an object has only one dimensional parameter in it, and that's Rs. So this should be somehow a function of Rs, and it should be a function of B, the impact parameter. So, right, if B is very, very big, you're sending a laser beam way far away as it passes some massive object. It's not going to deflect very much. That's sort of it, if you think about it. You can only tweak beta, and since alpha is an angle and has to be dimensionless, the only guess you could make, at least the simplest guess, is something that has to look like Rs over B. It shouldn't be proportional to B. It can't grow like some power with B. It should get smaller as B gets bigger. And if you just guess that it's simply inversely proportional to B, then the Rs has to go on top. And then the last thing is to actually work out the details, which requires a little bit of math to do, but it's not that bad. What you'd find is actually 2 times the Schwarzschild radius divided by B. And that, if you plug in what the Schwarzschild radius is, that means it's 4 gm over c squared times b. Fun fact, I believe that if you just use the Newtonian theory of gravity, right, if you use gmm over r squared, you'd say, well, light doesn't have mass, so why should it be gravitated at all? And so that's wrong. If you don't use gmm over r squared, but you at least acknowledge that there is this equivalence principle which seems to hold for everything, that all objects seem to fall at the same rate, and that should apply for photons, then you would calculate a deflection angle, this alpha, to be only Rs over B, or you'd get it to be 2 gm over c squared B. And it turns out that there's this extra factor, if you like, the multiplication by a factor of 2 is a result that only comes out of general relativity. And so, right, that's at least one huge difference between Newtonian theory and Einsteinian theory. Okay, anyway, that's what the deflection angle should be as a function of the mass of the object and the impact parameter B. And so let's just plug in some numbers and see what would happen for the sun. If, for the sun, you sent a laser beam, or if you like, you're looking at a star that's super, super close to the edge of the sun, then let's let that impact parameter actually be equal to the radius of the sun, or maybe just like a tiny bit bigger. The radius of the sun, I've, I guess, written down here 6.96 times 10 to the 5 kilometers. So I always think of that, I approximate this as 7 times 10 to the 5 kilometers, but let's keep the 3 digits there. Let's plug in the numbers. Alpha, therefore, I guess, is equal to a It's 2 times the Schwarzschild radius, which is 2.95 kilometers, and I'll divide that by the 6.96 times 10 to the 5 kilometers. This should be a dimensionless number. And it turns out, because I just did the calculation a second ago, this is approximately 8.477. I think that's actually good for sig figs, but check me on that. That should be that times 10 to the minus 6. And it's dimensionless, but this should be an angle, so this should have units of radians, right? If we want to convert this to degrees, and in particular into arc seconds to confirm the result in Riden, then what I should do is actually multiply this by, first let me convert to radians, so I'll put 180 degrees over pi radians, that's a conversion there. And then lastly, I know that in 1 degree there's 60 minutes, and in each minute there's 60 seconds, so I'm going to write this as 3,600 so-called arc seconds for every 1 degree. And if you work this out, I claim you should find this is approximately 1.75 or close to 2 arc seconds of bending for, again, this is light that just grazes by the sun. And, you know, the sort of classic example of the supposed observation made by, oh, what was his name? This British guy, I think. This is like in 1919, there was an observation of an eclipse. Look up the story. I'll remember it as soon as I'm done recording this. But anyway, the claim was that a star that was very nearby the position of the sun was seen to deflect by an angle that was consistent with Einstein's theory, although I think people will argue about whether the observation was actually statistically significant. Anyway, that's how things go. And so you can imagine now that, well, if you know about the positions of background objects and you're able to figure out the sort of impact parameter and also the angle at which the light gets deflected, then you can learn something about the mass of the object that did the gravitational lensing. I should also just kind of try to complete the picture. Imagine you had a bunch of parallel rays coming in, going past this massive object. So you might think, well, okay, like the ones that are really far away, they'll kind of do this, and maybe, you know, maybe they'll have deflected a little bit, but not too much. The ones that are, you know, even closer should deflect even more. I hope I don't draw this too crappily. Let me just point out something, right? You can kind of see where this is going. I guess some light actually hits the object, and some might get bent a heck of a lot. Wee. That one was terrible. Let me just get rid of that one. Let's not tell anyone about some of these. Okay. That's a nicer picture. Let's leave it there. Notice something, though. To the extent that you buy this, you know, picture that I'm drawing for you, if you are right here, in fact, if you're anywhere nearby the mass on the other side, so like, for example, right here, you will see two light rays, right, that came from here and here. And in general, what's going to happen is any image, you know, which is, you know, which is the result of lots and lots of light rays that are being emitted from it in all different directions, you'll find that images are distorted. And in extreme cases, you'll find that images really get stretched out and make arc-like shapes, or even make what are called Einstein rings, which is what happens when there's an object sort of directly behind the massive object doing the lensing. And so although the light that might normally go, you know, towards the object and crash into it, you wouldn't see, that's true, but you have to realize that there's some light that kind of just was on its way this way, but then due to the gravitational lensing, boom, ends up hitting you there. Boom, ends up hitting you there, and I'm only drawing this in 2 dimensions. You can imagine this is true in a bunch of different planes of orientation, and so you can actually get entire rings of light. And right, so what that will also mean, since you're getting more light than you otherwise would have in the absence of this mass, you'll get an amplification of flux. If you like, you're getting, depending on where the lensing object is, you are getting more photons per unit time than you otherwise would. And this is useful for making some observational constraints on actual candidates for dark matter. We'll get into that in a bit. But anyway, let me just point out that I hope that you have access to your book. There's a very good image in figure 7.6 in Riden. It's of Able 2218. You can see these nice arcs, which are gravitationally distorted images of galaxies behind this massive, rich cluster that's in the front doing the lensing. Right, so anyway, I guess I'm going to sort of leave it there, not going into too much detail, but you have to realize that with a decent model of what the images of galaxies should look like in the absence of a lens, like a big cluster, when you then look at the gravitational lensing produced by a cluster, you can, based on the angular separations from the cluster center, and based on the amount of image distortion, with a good enough model for what the image looked like before, one can infer how much mass is doing the gravitating, how much gravitational lensing mass there is in the cluster. And that is additional confirmation about the masses of these clusters, and additional confirmation that there's way more gravitating mass than there is in the form of stars and gas. Lastly, I should have hopefully given a link to a very fun little simulation where you can change the position of a background galaxy and see what the lensed image looks like as you move it around throughout the universe. So I guess that's it for now. Thanks for watching. Stay tuned for the next exciting video.